Welcome back to the second part of this lecture. What I'm going to be talking about now is an example of a probability distribution, the binomial distribution, which is an important example. And also it's a nice exercise in the application, once again, of sum and product rules, calculation of means and calculation of variances and things like that. So let us um, go for that now. I want to do my screen capture. Um, where am I? Here, change there, and now do that. Let's hope I got it right. Okay, very good. Uh, what we're going to consider is an event that can either happen or not happen. So let theta be the probability of an event alpha, and 1 minus theta be the probability of not alpha. Now you start seeing why it is that the binomial distribution is actually so common. Because whether alpha represents tossing a coin and getting heads or not heads, or alpha represents the atom decayed or did not decay, or whatever, or it's raining but not rain, or not raining, the number of situations where you have something happening or not is extremely common. Let us now ask for what happens if we look at a certain number of trials of this event happening or not. So we want, let's do it like this, we want the probability of the event alpha happening m times in n independent trials. So this is what defines the binomial distribution. You have an event that can happen or not happen, and then you have a number of independent trials. Whenever these conditions apply, you get you get a binomial distribution. And so the way we actually compute that is we say, well, we're going to say, suppose we have a sequence of n trials, and we get alpha, 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 m times, and then not alpha, and so on, n minus m times. Then you see that these are independent events, and what we're asking is for the probability of alpha and alpha and alpha m times. The probability of that is, the probability of this particular sequence is the product. These are all independent events, so it's just the probability of each one of these events. Here we go. That's the probability. Now you can see here also that if you have these alphas and not alphas in any other order, that would give you exactly the same probability. So the question that we ask next is, what is the probability that the m alphas are obtained in this particular sequence or in another sequence that is a permutation, or in yet another that is a permutation? clearly what we have to, when we want to compute the probability of m alphas in n trials, given that the probability for each trial is, for each success of alpha is theta, what we have to do is we have to sum, it's an OR, right? Where this is the disjunction. It's either this sequence or a different order or a different order or a different, we have to sum over all sequences this probability here, the probability of one sequence. So it's interesting that here then we are using the product rule, and here we're using, so for and here we're using the sum rule for or for events that are mutually exhaustive. Very good. How many sequences do we have? Because this obviously it's the same for everyone. The number of sequences, the number of, whoops, let me write this again. The number of sequences is, it's the number of permutations of n, capital N elements taken m by m. So this is the number. And this is n factorial divided by n factorial n minus m factorial. Very good. So we have a final answer here. The probability of getting m alphas in n trials is going to be given by this combinatorial coefficient. Theta m 1 minus theta n minus m. Very good. So now that we have the probability, what do we do with it? First remark. The number theta plays two roles. One of these roles is the fact that the probability of getting alpha, of getting one outcome alpha, when you do just one trial and the parameter theta takes that value, is theta itself. So one of the interpretations of theta is it's the probability of alpha in one trial. The other important thing about theta is that theta is a parameter that labels the probability distribution, the distribution Pm and theta. Why do I say this? Well, it's because if you look at the space of all binomial distributions, the space of all binomial distributions, that's a statistical manifold. So the statistical manifold, I just want you to become familiar with the lingo, the statistical manifold of all binomials is, well, it's one-dimensional. Theta goes from 0 to 1, and each point there, the point theta, represents a probability distribution. So later on, we're going to want to figure out the distance between two probability distributions, maybe between this one and that one, right? Two different probability distributions. We're going to want to figure out, is there a geometry? Well, this is a very simple space. It's one-dimensional, but we would like to figure out what is the geometry of this space. What are the distances here? Very good. So we have our binomial distribution. What we would like to do next is to be able to compute the expected value and the variance. And the way we're going to do this is, my purpose really here is to introduce a trick. So suppose we want to compute the expected value, and the way we do it is we sum for all values from 0 to n of the probability, which is this one, and we multiply m times the probability. So that's what expected value. And so what our challenge here is going to be to compute this summation. And there is a valuable trick to do this. The trick is to notice that if you take the derivative with respect to theta of theta to the m, you get an m in front. So if you take the derivative of this theta m with respect to theta, you get this m here. Now, of course, what you're getting here is m minus 1, so you spoil that object there. So let us multiply both sides by theta. And so the little formula that I'm going to be using here is that the theta d theta applied to theta m gives you theta m. So that's the little trick we're going to use here. When we do that, then m can be written as there is going to be the n m m theta m. So that's going to be theta d theta theta m 1 minus theta n minus m. So now you see we have a little bit of a problem here. The fact that this theta d theta does not depend on m means that I have the possibility of pulling this guy outside of the sum and then doing the summation of what remains without now having to bother about that m there. So what I'm going to do, and but obviously we can't do that, right? Because if we pull the d theta out, then the d theta will be acting not just on theta m, but also on that theta there, and that's going to screw everything up. So now, what we're going to do is we're going to do something. We can see the strategy of what's going on here, but we're going to have to manipulate these numbers a little bit differently. We're going to say the following. We don't want this d theta to act here, right? We do not want the d theta to act there. So what I'm going to say is the following. I'm going to define S, which is a function of theta and phi. It's this particular sum here. Like that, it's this sum n m theta m phi 1 minus phi theta minus m. Very good. Notice that what we want to compute, which is this, is going to be the function that we just have up here, the summation, evaluated at phi equals 1 minus theta. So let us just evaluate the sum S and then proceed to evaluate with phi equals 1 theta. So we're going to write S is the following: sum from m equals 0 to n, then we have the coefficient, then we have m, we have m theta m, that's theta dd theta acting on theta m, and then we have phi n minus m. Notice that now nothing prevents us from pulling this in front, and we have to evaluate the following sum. The beauty about this is that if we use the binomial theorem, this equation, this summation here, is the sum is the is given by the following: take theta, take phi, and take this to the power n. So when we actually do that, we get S theta phi is equal to theta dd theta theta plus phi to the power n. And this is something that we can compute, because this is just going to be, we have theta, then we take the dd theta of this, it's going to be theta plus phi to the power n minus 1. Am I doing this right? Oh, yes, and I have theta, I have this. I forgot the n in front. Take the derivative, you get n in front. And so this is our sum. And so now we're ready to evaluate m when we plug in phi equals 1 minus theta. We're going to get just that. So 2 remarks. First, this is the fact that we can actually do this trick using the binomial theorem is what gives the distribution its name. So the binomial distribution, it's because all the calculations are done making use of this trick of the binomial theorem. But there is another sort of interesting thing that we have here. When we have something like this, so note the following. When you have the summation m equals 0 to n m theta m1 minus theta n minus m, what do we have here? Here we are just adding the probabilities for all values of m. So what we are saying here is we're looking for the normalization of this probability. This is equal to 1. Probabilities are, well, you can actually prove this, right? This is going to be theta plus 1 minus theta all to the power n, which is 1 to the power n, which is 1. So what we have seen here is that the trick of computing these expected values has to do with figuring out how we do the normalization of, with expressions that have to do with the normalization of the probability distribution. And once you have the normalization factors, you can actually figure out everything else. This is one example of that we're going to find extremely useful over and over and over again. If you want to compute an expected value, the way to go is look for the partition function, right? So here we see it in a case that has nothing to do with statistical mechanics or with Boltzmann distributions or anything of the sort. But the trick is in fact, this is one of the few cases where we can actually compute expected values. You're going to try to figure out how you do an expected values to do expected value by taking the derivative of something, the derivative of a partition function. Very good. How do we compute the variance? The way to compute the variance, which is take the quantity, calculate deviations from the mean, take the square, and then average. So it is the average of the square of the deviations from the mean. We're going to write this in the following form. This is homework problem to figure out that this is equivalent. We already know this. This piece here is going to be, let me write it like this. It's what we have up there. This is going to be n theta squared. So now what we have to do is compute this guy here. So to compute that one, we're going to use the same trick. And the way we do this is we're going to say, well, we want to do the average. So we sum over all probabilities of m squared and multiply by the probability. The same trick as before suggests that we consider the following sum. Let me see, we're going to call this sum S prime. Here we go, we do the sum S prime. Very good. The sum S prime is going to be m squared sum over all m's n m theta m phi n minus m. The trick we use is to write this as m times theta m squared theta m. The trick we use is peel out one of the m's, and for the other m we do the same expression we had before. And now that we have this, bring in the m, and we're going to write this as theta d theta theta. So we're bringing this m here. So we repeat the same recipe. So then S theta phi is going to be theta d theta acting on theta d theta, and then we have the sum without the m's, which is just the binomial theorem. Now you have to be careful here that this d theta acts here, but this d theta acts both there and there. You have to keep track of all of those things. When you actually do that, the answer is pretty straightforward. You get that S prime theta phi. Let me see. I just jumped to the conclusion. The expected value of m squared is going to be this quantity S prime of theta phi when phi is evaluated at 1 minus theta, and the value is n theta squared. You just have to do it. Take the derivatives and do it. And this is what you get. The variance is m squared, which is the expression we have here, and you subtract m, the expected value of m squared, which is exactly this first term. So for the variance, we get n theta 1 minus theta. Just calculations, but the tricks are useful. You have plenty of homework to fool around with these things to get the feel for it. I'm sure you've seen this in one form or another before, but it's a good idea to remind ourselves how these tricks work. Let me see. What else do we have to say? Yes. When we do the actual RMS deviation, the standard deviation, we have to take the square root of this. There you go. Now, one of the things you see here is that the standard deviation grows when you increase the number of uh, trials. You can also see that if theta is equal to 0 or theta is equal to 1, then the standard deviation is 0. And that's obvious, right? If theta, the probability of one alpha, one outcome, is 1, you have complete certainty. So if theta is 0, you know every trial in this sequence is going to be alpha, 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 alpha. They're not going to be not alphas. And so, of course, the distribution is going to be infinitely narrow. There is absolutely no uncertainty. The other situation in which you have no uncertainty is when theta is equal to 1. The other way around, right? Alpha equals 0, you have no uncertainty. Theta equals 1, you have no uncertainty. Very good. I just said that delta m grows with n. You saw it there. However, this gives you the impression that the uncertainty is increasing, and that's completely correct. For some reason, this is not responding. There you go. For some reason, let's see, that's not strictly correct. While it is true that this increases, if you were to look at the relative growth of the width of the distribution divided by the actual mean expected value, then what you get is n theta 1 minus n theta for the RMS deviation divided by the expected value, which is n theta. And so the actual result here is that you get 1 minus theta divided by n theta square root. So that while the standard deviation grows with n, the relative uncertainty here, the relative standard deviation actually goes like 1 over the square root of n, which means it becomes relatively, the distribution becomes relatively sharper and sharper and sharper as n grows. What else do we have to say about this guy? No, I think that's about it. What I would like to do next is something uh, important. It's conceptually, it's central to everything that we want to study when we deal with probabilities. We want to compare the notion of probability and frequency. How are the two connected? And in the process of doing this, we want to derive the law of large numbers. The law of large numbers. Now, already here, we saw something interesting about large numbers. Uh, you are tossing a coin and you toss it many times. What is the expected value? It's n theta, yes. But what is the uncertainty in this? It's the numerator here, right? The numerator there. The numerator is increasing with n, so the actual error in your estimate is increasing. But relatively speaking, the ratio here is such that the the ratio goes down, goes to zero as n goes to infinity. So this is already an indication that although you do not really know what really is happening when you're tossing your coins, in the limit of large numbers, you can make assertions with a fair amount of certainty. This is what's going to be at the very foundation of being able to do thermodynamics and do use statistical methods when you have a large number of particles. So it's the kind of thing that matters because in a context in which you have very limited information, you can actually answer some questions with a fair degree of certainty in some special cases, in particular case of having large numbers. So this is how it works. First, let us look at the connection between probability and frequency. There is a certain tendency to think that if you toss a coin a billion times and you get half a billion uh, heads, then the probability of heads is 1/2. Okay, that's a good idea. And that's why that is an insidious notion. It's actually all right, but conceptually it's totally wrong. And so that's what we want to do in this particular section of the class. Analyze in a little bit more detail why it is that a probability and a frequency are related, but they're not the same thing. So that's absolutely crucial, right? Right? If the only notion of probability you have is that it's going to be some kind of frequency, then you need many trials in order to define probability. If you have this idea that you can only talk about things that can be defined operationally through experiment, then you're stuck because there is no way to estimate the probability except by doing many trials, right? So these conceptual issues are going to be absolutely crucial to get a notion of probability that can be applied in full generality. Very good. Let's go here. So suppose that we have you're tossing your coins, and this is M, and this is the probability. Yes, the probability of M, and this goes all the way from 0 to n. And so you're going to, this is, obviously this is discrete and I shouldn't write it as a curve, but you're going to get some kind of curve like that. Some kind of curve like that. So what I'm going to do now, and please notice that what are the allowed values? When you take a coin and you flip it n times, what are the allowed results? Well, the allowed results is 1, 2, 3, well, n minus 1, n. You get all of those results are possible. It is possible. It is possible to throw a coin a billion times and get one heads, and that's it. It is possible. It's here. The probability is not zero. Probability is not zero. But now let's look at this in terms of frequency. In terms of frequencies, that's just the ratio of the number of outcomes uh, of alphas divided by n. And here we're going to look at the probability of that particular frequency. Well, clearly it goes from 0. If I divide m by n, it goes from 0 to 1. And the actual values here are going to be 1 over n, 2 over n, and so on until you get to down here and you have n minus 1 over n. And the distribution, of course, is going to be, the probability is exactly the same, something like that. As n grows, this becomes sharper. So the expected value there, expected value of the frequency is going to be the expected value of m over n. If you, this n, capital N is just a constant, I can pull it out of the calculation of expected value. This is n, the expected value is n theta, and we have this very interesting result that the expected value of the frequency is the probability of success in a single trial. So while it is true that f is not the probability theta, why is that? Because f can be 0, f can be 1 over n, f can be 2 over n, f can take any of those values, and theta is what's going to be just this value here. So while it is true that f is not the same as theta, it is definitely true also that the expected value of f is theta. Interesting. Does this mean, because this is a probability, it is the probability of getting one alpha in one trial when the parameter is theta, right? If this is true, could we possibly define probability as the expected value of the frequency? Well, not quite. It is true that this equation here is correct, but we cannot define probability as being an expected value. And the reason is that the expected value itself uses the concept of probability. And so defining probabilities in terms of expected values that employ themselves called probabilities ends up being circular. So that doesn't work. Very good. What happens when n becomes large? When n becomes large, this probability becomes the width of the distribution becomes narrower and narrower. This peak goes up and these guys here go down. And so let us figure out what the width is going to be. Let me just write it like that. The standard deviation for the frequency is going to be the standard deviation of this quantity here, and that standard deviation, because n is a constant, is we can pull it out of all of those summations, and this is just going to be the look at the formula that we had here before. This formula here. Oops, sorry. This formula here. So for the standard deviation of m, we have n theta 1 minus theta. Okay, let's write that down. N theta 1 minus theta square root all divided by n. So the variance, the standard deviation for the frequency is going to be theta 1 minus theta divided by n, all taking square root, which is proportional to 1 minus, 1 over the square root. While, well, no, that's what it is. So you can see here that the effect of this increasing the number of trials is to make the distribution sharper and sharper and sharper. This goes down and that one goes up. Okay. With this, we sort of reach some kind of conclusion concerning the connection between frequencies and probabilities. Frequency is not probability, but the expected value of the frequency matches probability. And that's why when the distribution is sufficiently narrow, when you have taken a sufficiently large number of trials, that's why we can sort of like replace one by the other. Now, it's true you can do that, but you have to be very careful not to make conceptual mistakes. What I would like to do next is repeat these calculations, or repeat these ideas in a more in a way that is of more general applicability. We're going to do it like this. We're going to study the law of large numbers. In such a way that we can apply it to not just binomial distributions, but more generally. And so it goes like this. We start by introducing what is called the Chebyshev inequality. The inequality works like this. This is it's actually extremely elegant, and it goes like this. Suppose that you have a variable x, and we, oops, let's go back, and the probability of x being contained, let me write it like this. The probability of the capital X to be contained between X and, so the variable is capital X and X plus dx. We're going to call this rho X dx. So basically we say, well, we have a distribution for this variable x, and we want to figure out the probability that it lands within a certain range, x plus the x. Here is the total probability, and that's given by the value of rho, the density, multiplied by the interval. Very good. So now that we have our formula, let's write what the variance is. Here's the variance of x. The variance of x is going to be the average of x minus expected value squared rho x dx. And we have to sum over all x's. Now, here comes the inequality. Whatever this is going to be bigger if I here take this quantity, the same quantity, it's the same integral, but notice that what's going on with these quantities here is that this is positive, it's a square, this is a probability density, it's also positive. Everything here is positive. So what I'm going to do is sum, not over all x's, but I'm going to eliminate part of the range. I'm going to eliminate the condition. The condition is going to be that I'm only going to sum for situations where x differs from the mean by more than an epsilon. If x differs from the mean by more, that's the region I'm adding. I'm subtracting the part when x is really close to the minimum. But because everything is positive, then you get that the left-hand side is bigger. Very good. Notice that because what I am including here are only terms where this is bigger than epsilon, I can say that this here is bigger. I'm going to replace the right-hand side by something that's even smaller. And I'm going to replace it by something that's smaller when I say it's the smallest value of this quantity. The smallest value of that quantity is epsilon squared. And now I'm going to integrate here x. I continue to integrate. Like so. Now what's amusing about this expression is that this is the probability that the quantity x differs from the expected value by more than epsilon, right? I'm using the sum rule. It's this quantity differs more than epsilon by a little bit, or by more, or by more, or by more. Do you notice the term or there? So I'm adding over all that, and that's why you get the summation. So conclusion, the probability that x differs from the expected value by more than epsilon is, let me see, this here is on the left side, is less than delta x squared, the variance, divided by epsilon squared. There you have the Chebyshev inequality. What this is saying is that x, the probability that, well, you can read it, right? The probability that x differs from the expected value by an amount that's larger than this will, of course, become smaller and smaller the more that you make epsilon bigger and bigger. That's what that says. So now, this is just an expression, a theorem. We just derived it, Chebyshev. And so now we're going to use it to derive the Bernoulli law of large numbers. And this is the way it works, Bernoulli's theorem. Maybe, shall I do it here or in the next page? Yes, let's do it in the next page. Bernoulli's theorem. Also known as the law of large numbers. Bernoulli's theorem says, well, what if we look at the binomial distribution and we look at the frequency? Yes, that's the frequency. This is n theta divided by n. So we have that the expected value is theta. And we also have a variance, which we computed before. And the variance is theta 1 minus theta divided by n. So what Bernoulli's theorem says is the following. Just substitute the expected value of the frequency. Well, substitute the quantity x being a frequency, expected value of the frequency, and here we have the variance of the frequency. So Bernoulli's theorem says the following. The probability that f differs from the expected value of f, which is theta, by a quantity bigger than epsilon, is going to be less than the frequency, the variance, divided, here's the variance, divided by epsilon squared. Clearly, as n goes to infinity, the probability, the quantity on the right hand side goes to 0. So the probability that you differ from the mean by any quantity actually goes to 0, right? So the distribution is getting narrower and narrower. Now, silly remark concerning the history. Why does Bernoulli get his theorem from just a silly application like this to the Chebyshev inequality, right? Obviously, all the hard work was done by the Chebyshev inequality. Well, consider this. Bernoulli lived in the 1700s, the 18th century, and Chebyshev is 19th century. So Bernoulli derived this way before Chebyshev, and Chebyshev just realized that the derivation was actually very simple if you use his inequality. Let me rewrite this formula that we have here in yet another way. So what this is saying is that the probability that f lies in the interval theta minus epsilon theta plus epsilon goes to 1 as n goes to infinity. Let me see. Here we're saying the probability that f differs from theta by something bigger. In other words, that f is outside this range. That probability goes to 0. So the probability that you're inside this range goes to 1. And so we can write this as follows. The limit as n goes to infinity of the probability of f minus theta being smaller than epsilon is less than, sorry, uh, let me put here, in n trials is 1. So that's another way to write that formula when we only focus on the limit, that formula when we only focus on the limit for large n. Does this mean that f goes to theta? Does this mean that the limit as n goes to infinity of f is equal to theta? The answer to that is no. F does not tend to theta because, well, there is no function f as a function of capital M. No function f of n, so we can take so let me write it like this. No function f, no function f equals m as a function of n divided by n, so we take the limit. This is not defined. There is no such thing as a m as a function of n. Remember, m takes all possible values. So this doesn't it doesn't make sense to take the limit, right? It's not like you try to compute the limit and the limit is infinity or it's zero or it doesn't no. It's even worse than that. It gets bad before you try to take the limit. So the proper language that we use to describe these ideas, clearly there is something here when we write these expressions like this one here, this expression or that expression, there is something that tells you it's moving in that direction, right? It's f becomes, when you take lots of large n, f is sort of like getting closer, getting closer. How do we say that without cheating? This is not what we can say. The language that is used by mathematicians and statisticians is the following. The correct language to express this intuitive notion that for a very large number of trials, the frequency is actually something, the observed frequency is actually the probability, is that f tends to theta. Wait a minute, this looks bad. Isn't that exactly what I was saying here? No. We say that f tends to theta in probability. This is the term, this is the language that you use. It is not that f tends to theta. It is rather that the probability of theta being different, the probability of f being different from theta goes to 0. So this is what we express when we say you have the probability distribution for a finite n, and the expected value here is theta, and this goes all the way from 0 to 1, and these are the frequencies, right? As n increases, it is not that this axis here somehow shrinks. It's rather that the probability goes to 0 out there and increases here. So it f tends to theta in probability. It is not f that tends anywhere, it is the probabilities that tend somewhere, because the probabilities are the ones that for which we have a function. Let me do an example of this. So this is crucial. This language is important. We're going to use it. It is not that f tends to something, it's rather that the probabilities of f tend to something. So suppose that we do the generalization that goes beyond the binomial case. You see, when we did this and we applied for Bernoulli's theorem, this is still binomial. We were using the expressions for the binomial distribution. So what I would like to do next is to go beyond the binomial distribution, and this is how we do it. We're going to say, suppose you have a variable x. This is a variable x, and it so happens that the variable x comes from having the sum of a large number r equals 1 to n of contributions that are clearly the contributions when you consider x divided by n, and later we consider n being large. It's x is the sum of a large number of small contributions. What can we say about this variable x? Let us assume now that it's not just a binomial distribution. It's any distribution, but we have to say something about these guys. So we're going to say where the expected value of each one of these guys happens to be known. So whatever the distribution for the xr's is, we know the expected value and we know the variance. The variance of xr is equal to, and we're going to write this as delta xr squared, like that, and this is equal to sigma squared. So all we really need to know about this distribution for the x's is the mean and the variance. What can we say here? Suppose that this x's, oh yes, it is. We need to know one more thing. Also, assume that the xr's are independent. When they happen to be independent, we can actually go ahead and try to compute expected values and variances, and we can use Chebyshev's inequality to see what happens when n is large and all of that. So let me do that, and it goes like this. The expected value of x is going to be 1 over n, the expected value of all the xr's, and each one of these guys is a mu, and there are n of them, so the result is mu. Then we can compute the variance. How do you compute the variance? Okay, so now this is a little bit more difficult, but I'm going to give you a theorem, and you're going to prove this theorem in one of the homework problems. The homework problem says that the variance of two variables that are independent these two variables are independent. The variable variance of the sum. Now remember, this is highly non-trivial because these guys are, when you take the averages that involve the variance, these averages are being squared, right? So this is going to be the variance of x1 plus variance of x2. By the way, this is one of the reasons why, remember when we defined the variance and I said, listen, the variance, you could define the width of the distribution in many different ways, but the variance is like really, really convenient. This is the reason why it is convenient. The variance of a sum of independent variables is the sum of the variances of each one of the variables. Very good. When we do that, then the variance of x of the sum up here is going to be 1 over n, the sum of the variances of each one of these variables. And so we go from 1 to n, and the variance of each one of the here we have a summation. Yes, let's proceed. Each one of these guys is going to be sigma squared. Let me see, am I doing this right? Yes, okay. I made a mistake here. That's what happens when I'm trying to rush things. This is the sum of the variances of x r over n. And now what we have here is n terms, and the variance of xr over n is going to be sigma divided by n all squared, so that the variance of the sum is going to be sigma squared over n. Very good. We have the average, we have the variance, and now we can apply the Chebyshev inequality, and we get the following. We get that the probability that the quantity x differs from the mean by something that is bigger than an epsilon in n, when you sum n times, is going to be less than the variance divided by epsilon squared. So this is something that has nothing to do now with the binomial distribution, but it's still nevertheless true that the limit as n goes to infinity of the probability that x differs from mu by a quantity that's bigger than epsilon is 0, or the limit that as n goes to infinity, the probability that you differ from the mean by a quantity that's less than an epsilon in n terms is equal to 1. So the probability that you're going to, the x is going to be very close to, that the sum x is going to be very close to the mean, goes to 1. And this we represent by saying x goes to mu in probability. Perfect. Time to stop here. What we're going to do next class is we have we have dealt with one of the paradigms of probability here, the binomial distribution. Next class, we're going to start exploring the Gaussian distribution, which is another one of the probability distributions that appears like everywhere. See you next time.